Yeah, it works. Good morning, everybody. Welcome to the last day of this conference. And I will be the chairman today. And our first speaker is Tulay. Please, Tulay.
First, thank you for the invitation. It's a great pleasure to be here and represent my country in a sense. And also, I'm in the computational science part of the mathematics. So, and as far as I see, there is no computational presentation yet. So, I'm glad that it will be different, or that will be another color in the palette. And I'll start with mentioning my advisor. She passed away very recently, and she was my advisor for 6 years, and she was a really respected mathematician in the field of symbolic computation. And she was from Hungary, so maybe she would be here. So I wanted to just mention as a great female mathematician. And this work, most of the works I will present here, it was with her. So I have to be obligated to just mention her name. In the computational part, how we approach problems is a little bit different than the pure mathematics. So we use pure mathematics, we have to use it, but we have to focus on the computational part and how we can actually compute stuff. Sometimes the computation has tricky parts. Sometimes doing the computation by hand can be more efficient than the computers, but sometimes having your computer help will reduce the time by years. So how we do in the computation in general, how we approach problems, has three parts. First is the constructive method part. So method part is basically pure mathematics. So usually in the symbolic part we use algebra or the other part analysis, but we do lots of pure part. And then after we construct the methods, we use algorithms to design how to tell the method to computers. So in the design algorithm part, we move from mathematics to computer science part. So how the computer works, how we can tell, or how we can make the computer do the work for us. And on the third part, after we're done with algorithms and implementation and get some experimental results, then we need to actually have some ideas what is the results representing and how we can actually get the benefit from the computation. And then we analyze the results, and sometimes we also build some new theorems based on those results. So it kind of goes in a cycle, like pure theory, some computer science and implementation on the computer, then we go to pure math. So it's like a cycle. And we use these three approaches and the problems on polynomials. Polynomials is my specific area of interest. It can be something else, but in my area we are working on polynomials. And we use numeric and symbolic techniques together. So the ultimate goal is to find robust and efficient algorithms to solve problems. Sometimes some algorithms are quite straightforward from the theory, but when you try to write it as when you go into the algorithm design part, it's not really useful, or it's not efficient, or maybe it just goes in a loop or something. Then you need to design it and optimize it. And then after you actually design and work with the algorithms, you also need to worry about the complexity of the algorithms. The complexity is how efficient is the algorithm is, or how computable. So these tools are mainly the tools I use for my research and for symbolic and numerical computation. So in the first part is the algebra part is coming for the symbolic computation. Abstract algebra is the tool, and algebraic geometry is my main tool because I work on polynomials. And also linear algebra and matrix theory are the tools I usually use for algorithm design part. And the analysis is coming from convergence and error analysis and some numerical analysis for algorithm design, and just build up the iterations or recursions. And for computer science, I have to know what kind of data structure I'm working on. So if I use symbols, or if I use integers, or if I use some decimals with some certain precision, everything will change. So I have to know what kind of data structure I'm working on. And also algorithm design and analysis part coming from computer science. Complex theory is the heavy part after designing the algorithms. And graph theory is a very useful tool, so we don't know where graph theory is going to pop up. So graph theory is something I didn't think I would use, but I still use in some interesting places. And optimization is another interesting tool by graph theory. In some places, when I try to optimize stuff, even if it's an algebraic or some discrete structure, I ended up in optimization many times, so it's another useful tool we use. And then we do the implementation. And the implementation, C or C++, C#, the other types of C, Python, MATLAB, Maple, SageMath, Vertini, these are the tools I use, but most of the people in the symbol computation now actually more in SageMath. SageMath is a Python-based program, so it is basically Python syntax, but it has many big libraries in finite fields and in polynomial rings, so you don't have to worry about writing down properties of those structures. You just call them from other libraries. So SageMath is an open source, and you can even contribute to that. They have like many places you can contribute as a pure mathematician or as a programmer. So I heavily use SageMath, and Vertini is a very specific tool I use for my research. So now let me tell you what's the difference between the numerical computation and symbolic computation, because they are two really different approaches. So in the numerical computation, this is what we are familiar with. When you have a calculator, what you do is a numerical computation. So let's say you divide 1 by 3 in your calculator, and just gives you 0.333, and number of trees is the numbers here. There will be some finite number of trees, like 16 is the very standard number. So it will just cut off from there, right? So it will be just this kind of number you will end up with. But if you're in a symbolic computation, it will keep it as a symbol, as 1.1/3. So it's not going to treat that number as a floating point number or as a decimal. It will just keep it as a symbol. If you want to check if your computation dividing 1 by 3 is the computation we know well at least. So if you want to check if the computation was correct, what would you do? Is just multiply that by 3 back, right? But if you multiply this number by 3, you're not going to get 1 back, right? Because there will be some error, because we cut off 3 at some point. So we neglected, there was a threshold. So the part you have will be the sign of the error. So you can actually guess your error. You can control your error if you know where you're cutting or what you're doing. But if you have 1/3, the symbolic computation will give you 1 exactly. So there's no error in the symbolic computation. It's basically what you're doing by hand, but you just manipulate the computer to do what you're doing by hand. So the computation has some error here and is exact. And in this line, the natural question arises, why we don't use symbolic computation all the time then if it is exact? So one of the main reasons is the architecture of the computers we have now. So the computers are based on, we all heard that zeros and ones, right? So zeros and ones, the structure, the architecture, how it is designed in the electronical part, which I have no idea. And the numbers, how they are kept, are floating point numbers as a representation of real numbers that we will see in the next slide. And the computer is designed to do that computation in a way that when you add up numbers, it will just keep one certain part, and when you do the multiplication and addition, these are the two main operations to do. The computer, since you give something, this one is something computer knows and how it works, then everything will be just one operation. But when you want to do this computation here, okay, this is one operation for computer. So it's a symbol, so it needs to do some other stuff, some more complicated stuff to get back to the result of 1. So it's, even with this simple computation, the time difference is significant. I mean, significant is very small here, but still you can see it. So this is a lot fast, or maybe I should have used the word efficient. But this simple computation part is not efficient, so we don't really use it all the time. So, but there is one other thing of the, now, I kind of took side of the simple computation, but now let me tell you why we need numerical computation, or actually numerical computation is more suitable for many things. Also in real life, like, let's say I have one chalk, okay, but let's say I have this chalk. If I divided one piece by 3 pieces, there is no way I can get 3 equal pieces, right? In real world, in the atomic level, so there's no equation. Nothing is equal actually. So there's always some error in anything we do. So the numerical computation, if we can actually control the error, that is definitely a better representation of our real world. But we need to really worry about the error. Let me give you one example, and like every once in a while, maybe in a couple of years, we hear that kind of news. Okay, there was a satellite that was thrown to the outer space, but then it's fallen into the ocean. These kind of things actually, like in the NASA, they have NASA reports on most of those stuff, and most of them are because of that numerical errors actually. So it can cause millions of dollars actually. So, but if you can control, of course, the outer space, like our Earth is surrounded by lots of trash satellites, so we can actually, throw stuff. So we can control it actually. But if we cannot, it can cause very big problems. So another thing I want to mention is the real numbers. Like real numbers, we call them real, but we all know that they are not real, right? So, I mean, how real are real numbers is a big question, and how we can actually use them in the actual world versus the theory. Because in theory, we have the real line, and it's full of numbers. But if we look at them, every single point, we can find the number, and if we can find the number close to that, we will find another number in between. So it's in theory, but in real life, we are limited. We cannot do that. So in theory, actual simple computation is kind of representative of that theory world, or our mostly algebra. But the numerical computation is more of a representation of the real world, because in real world we are all defected, we all have errors in everything. So if we can control the numerical computation, that's the tool to use. But as mathematicians, actually even pure mathematicians, we need some theory. So in the theory part, when we need the computation, the symbolic part would be more useful. So let me talk a little bit about numerical computation and floating point numbers. So in the numerical computation, we compute with numerical approximations. And these approximations, we use floating point numbers in computers. So the definition of, this is the very definition of floating point numbers. They are representation of real numbers in computers. But computers has a limited memory and limited, everything is limited in the computer. Also, it's limited in our minds, but in the real life, we have infinitely many numbers. So we cannot represent every single real number on computer. We don't have everything in computer. But we have some representations, and we use them with certain precision. So the floating point numbers are subset. Of course, we cannot represent everything. Real numbers using an integer with a fixed precision, and let me show you this example. So in this number, this can be a floating point number, and this part is called, the integer part is called significant, and 10 to the minus 3 part, 10 is the base, so this number is base 10, and the minus 3 here is the exponent we have now, and this number here, we call this is a floating point number in base 10 5 digits of precision because there are 5 integers here. So, but in a computer, if you are in a, if you fix the precision to 5, and you want to just add up this number, okay, it's another 5-digit precision floating point number. If you add this number to this number, what you end up is a 6 digit. So 6 digit precision. So in the computer, if you fix the precision to 5 digits, it will round this number to this number. So even with this simple computation, your result is not going to be exact. So in the computers we have now, mostly the precision is fixed to 16 digits. Sometimes you can extend it, actually, you can change it, but we have still limited precision. So we need to watch out this kind of errors or roundings. This is called rounding error, but we can also have representation error. The representation error can come from 0.3333 because we cut off at some point. So representation of 1.1/3 is also has some error. So there are many different kinds of errors. And in the standard computers we have, what we use is a standard called IEEE 754, and our computers now are usually 64-bit. It means we have double precision. In that bits we have, I think if I remember correctly, there's 1 bit for the sign, is plus or minus, and there's 52 digits for the integer part, and for 10 to the or 2 sometimes, it was, I think, 11. If I remember correct. Yeah, it's 11, 52 plus 1 is 64. So we have 64 bits, and these are how they result in that the standard 54. So this is how we can actually store the numbers. So we don't have representation of every single real number. In the symbolic computation, what we do is actually we manipulate the computer to keep some fractions or some irrational numbers as they are, as symbols. So we basically, what we do is algebraic manipulation. So it was actually the first name for the symbolic computation. When they started, they called it algebraic manipulation first. So, it's not very readable, sorry. But the symbolic computation has 3 main parts. The one part is computer algebra. So the computer algebra can be algebraic geometry, number theory, algebraic topology, coding theory. It's like a huge area. Then there's an intersection with the mathematical software. We have computer algebra systems. And the other big chunk is computational logic. So the computational logic part is also very interesting applications. If I had time, I would like to talk about that. Now, the big hype in that area is building proof assistants. So we are going to how computers can prove theorems is the big question. They are actually working on that now. We have actually many questions from industry or technology or other sciences, then applications in natural sciences, and application in basic or theoretical research. It is also used also symbolic computation in big algebra related subjects, and also in computer science we use that a lot. So applied or computational algebraic geometry is the part I'm working on, and there are many people in this area. And in linear algebra, in cryptography is also another research area of mine. I work on some cryptography systems. And fast arithmetic is interesting area here. And algebraic topology, coding theory, these are the people who work on the computational side of these areas now. So for the applied algebraic geometry, so we have a bi-weekly conference. It's actually a really big one. So last summer it was in Eindhoven, and it was after the COVID. It was the first face-to-face conference, and everything was the conference was huge. We were at least 700 people face-to-face, and we also had some online participants. Everyone was there, so it was really amazing to see how it's improving so fast. Because that conference started when I was a PhD student in the United States, and it was the first conference. It was organized in my institution, but I was just a first-year PhD student, and the things I saw there and the things I saw this year is really amazing. So, and how we can actually use them together. So, the Leon Z is one of the oldest member of the committee. She's very old, and she works in China. And there is a little booklet about symbolic numerical computation, and this is what she said in the preface of the book. The growing demand of spend, accuracy, and reliability. The reliable part is coming from symbolic computation. In scientific and engineering computation has been accelerating the merging of symbolic and numerical computations. And these two types of computation coexist in mathematics, yet are separated in traditional research of mathematical computation. And so how we can use it, both of them can have different parts. Like some mathematical modeling people actually using it for in some polynomial models. They use lots of symbolic computation in one part, but when they need efficiency, then they cannot really compete with other, some other parts. Then they start using symbolic and numeric together. And some applications, there are many applications, but these are the ones I'm interested in. I have seen a lot. Is the approximate GCDs of systems, multivariate polynomial system solving, and this is one of my area, and interpolation, and in multivariate interpolation, everything gets so messy so quickly, and simple computation controls it very well. And algebraic statistics is also a very new area. People use symbol computation. Quantifier elimination, symbolic algebraic decomposition, and linear algebra on finite fields. And first arithmetic use symbolic and numeric computation together. So I will now start to give you an example of how we use both of them together. So we start with polynomial roots that we are all familiar. So let's say you solve a polynomial. Okay, it can be as simple as 3x minus 1. Okay, and when you solve it, this is the same thing the example I just gave, right? You will get 0.333 as a solution, but it has some precision. And if you plug it back in to the polynomial, you're not going to get 0. So how can you decide that it was actually good? Even plugging back in is not working. But we know that, okay, we know this was a simple example, and we know this is 1/3, and it's actually a root. But let's say you have a multivariate polynomial with lots of variables, or maybe you can have polynomial systems with many polynomials with many variables, and it's not easy to see. Sometimes when you do the numerical computation, the outputs are floating point numbers, like something point something something something, and the computer system gives you those numbers, and you just have the numbers, and you have no idea if they are really the solutions or not. Okay, this is just a numerical part. There's no symbolic involved in it. So this numerical computation is very efficient. So in the differential equation systems, in polynomial systems, in multivariate big systems, there are many efficient methods. But most of them, the biggest ones, are not certified. So what you get as a result are basically just a bunch of numbers. You have to trust the computer or the algorithm, or sometimes they can be wrong, and that satellite can fall into the ocean and stuff. So the numbers are sometimes just really meaningless. But sometimes you have the bounds and stuff, you can usually guess if it is correct thing or not. But polynomial root certification is one of the applications of symbolic numeric computation. We use them together. And this is one of the main problems we have in the area. So also in the efficient methods, the numerical methods, the results are, if you're doing something practical, okay, if there's some robotic, like robotic models, when they model the movements of the robots, they end up with a polynomial, multivariate polynomial systems, and the results are usually good. In practice, the engineers are actually satisfied with the results mostly. But even if sometimes the really like precision needed applications aside, most of the engineers are happy with the results. But if you're a mathematician and if you want to use your results in your other theoretical parts, you continue your research, you solve something, and the result of that polynomial system, let's say you will use in another theory, or you want to test if it works. But if it is not certified, it's not going to be useful. You cannot convince other people or other mathematicians that their results were valid. So the certification is actually very crucial for theoretical mathematicians. And one of my friends is working on that cylindrical decomposition thing, and she just keeps solving polynomial systems on her theory. And for each time, each step, she's actually the one I know. She used my results, but sometimes the engineers are happy with their results. They are not really worried. But there's one application that I was really amazed to learn is when they have robotic arm surgery robots. That robots, they have just arm and they do the surgeries. And in that kind of, they're still testing, I think. But in that kind of application, the precision is so important. The precision, what I mean is, sometimes they want to cut certain place. Sometimes they don't want to cut certain vein, let's say. So they want to stay in a certain area. That is also one of the application of the polynomial root certification. Not always you want to certify that number is the result, but sometimes you want to see if there is no solution in one area. That can be also another interest. So, and if you're in a single computation world, what you can do is just plugging back in would work, right? So if you're in this kind of computation, if you want to make sure that your result is the correct one, the exact one, then single computation is the way to go. So, yeah, I already answered that question. So let me give you the just very common notation. So what I use here is the multi-index notation. So when I write just x to the d, I mean something multivariate. So it will be a vector of the monomials, and the monomials will be based on the variables and some vector of the exponent. So xt is not just xt. Also, when I define the polynomial based on that multi-index notation, when I write as a sub d, x to the d, what I mean here is this is just a monomial. It's not just one variable, and this is the coefficient of that term. So it will be just term of the sum of d terms. And when I say polynomial system, I mean multivariate polynomials, and we want to solve all of them simultaneously. We are interested in the common solution of many polynomials. And the ideal is when I use the letter that's expressed with I mean the ideal generated by the polynomials. And now I can define what is the certification problem in a formal way. So we are given the polynomial system, okay, on K, and the variety is 0-dimensional here. Okay, the solutions are isolated points size, and we are given the approximate roots of f as these. Okay, the size are the exact roots that we don't know yet, but these are the approximate roots that we are given. So you solve the polynomial system, you are given some numbers as solution, and you want to certify them, or you can have different purposes. And so these are floating point numbers because these are results of, these are approximate roots, so these are results of numerical computations. And let's say z star is one of them. And and also we are given a rational number of epsilon. This is the precision, or this is it decides the area we are interested in. It decides the size of the area. And the goal is to certify that there exists an exact root psi of f in the epsilon neighborhood of a given approximate solution z star. Okay, so we are just looking at this open ball, and we want to certify that this ball has actually,
Just one question, why epsilon needs to be rational? Isn't it enough only to be positive?
It can be positive, it can be any number.
Actually,
but here
it has to be positive because of the definition of the ball.
Yes,
Ah,
yes,
yes, okay.
this is here.
But it can be a real positive number.
Yes, but we can write because we are given floating point numbers, and we can write the floating point numbers as rationals. This is actually why we use these words. But I know this is not familiar, but this will play a role in the later, because what I worked on was all rationals. So this is my input actually. Maybe that can be something else. So in this open ball, we are given this z star and epsilon, but we don't know this one. Okay, this is not here actually. We have no idea about this. Okay, but we will certify that actually there is an exact root in the neighborhood without any knowledge of the exact root. So there are some solution methods or some approaches on the certification problem. If you're on reals and if you have a square system or well constrained system, if you have the number of variables and the number of polynomials are the same, Smith's alpha theory actually gave a really nice tool. Based on his theory, they constructed a method. Sofia and Einstein. Einstein was my co-advisor. So they did that. They actually implemented. It was the first time ever. So theory was there, Smith's alpha theory, but in 2012 they used C and C++, and they actually wrote the program. They did some algorithmic approach. So they had the theory and they just did the rest of the steps I just listed in the first slide. So they did the computation and they end up with a really package that you can certify your roots. And it was first time ever, so people were like, okay, so numerical computation and symbol computation can be used together. So that implementation was a big step, and it was kind of starting the computational part of polynomial certification. And but you need to have this method, this Smith's alpha theory, is based on Newton method. So Newton method is an iterative method, and for each iteration you get closer to the root by one. So it's a very numerical method, but they use some other theories to certify the roots of polynomial systems. And their theory of how they did in 2012 is actually a very improved version of alpha theory, but it's based on Newton theory, Newton method. And in 2018, with my advisors, what we did is actually we extended this approach to the overdetermined and singular systems, because it was not working on overdetermined systems. And overdetermined systems are the systems they consider here are called well constraints. The systems we use here are called ill-conditioned systems. So ill-conditioned systems means you cannot plug the numbers back in because it's overdetermined, and a little bit of error in the root cannot get your zero back. So it doesn't work. Like most of the theory, like really nice polynomial tools are not really working well in the numerical part with overdetermined and singular systems. So it was my PhD, and how we did is we used lots of algebraic geometry on some overdetermined systems, and we kind of found an equivalent system, equivalent well-constrained system. And the equivalency was the more theoretical part, the algebraic geometry part. And then so we could use the Smith's theory. Also for singular systems, if you have some roots with multiplicities, it's also a big problem because you cannot really plug numbers back in, nothing really works well. And Newton method doesn't work, so since these things are all on Newton methods, the other system had to be converged to something else that we can use Newton methods. So this was my PhD work, but after my PhD, I came back to, let me also talk about this application. This is my favorite application of the area. After they did the alpha certified package, actually this was used to prove a theorem by pure mathematicians. The theorem, the problem was, is it possible in three-dimensional space for 7 infinite circular cylinders of unit radius, each to touch all of the others? So 7 is the number such as the so I don't know what that means. But at the end, those guys, Ozodi, Lee, and Vanya, they actually used that package to prove a theorem, and they actually came up with a solution. So, and these two, actually there are more solutions, but these are the two of them. So there are 7 cylinders, and they all touch each other. And this was, this solution was using the alpha certified theory. So some theoretical mathematicians also use this approach. So yes, after all these methods, after my graduation, after I came back to Turkey, we start to work on something else, another method. But this method also works on rationals. With the rationals are actually not really a restriction, because all the floating points can be written as a rational number, and we can do the theoretical part. So this is not a bad assumption. But what we came up with here is a different kind of method for just real roots. Here we just dive into real algebraic geometry. So the method we came up with is called, we call it the zero-dimensional Hermit method, because it's based on Hermit's really old work. And this method, one of the good things about this method is not related to Newton method at all. So we don't need to worry about convergence of Newton method, but we need to worry about some other stuff. So I will present how we did that in summary. So our assumption is the ideal is 0 dimension. So we want separate, isolated solutions. We don't want any higher dimensional things. Actually, that can be another step. Maybe we will work on it someday. But I don't know. For now, and the 0 dimension case is actually the case engineers are mostly interested. Most of the applications, what they are interested in the 0 dimension, all isolated points, and they want to know if the isolated points are in the certain area or not. Our third author in the previous papers, Jonathan, was actually an American citizen, but my advisor was Hungarian and I was Turkish, so we were not American citizens. And Jonathan was involved in some projects in DARPA, in Army of the United States, and actually they used some of our results in some simulations. This is the only information they gave us, but the rest was we were not allowed to know. So I don't know how they used my results from my PhD, but my advisor just told me they used those results in simulators and when they educate the pilots. This is all I know. And but here this method it was just Agnes and me, and because this part was more real algebraic geometry part, and Agnes was in the real algebraic geometry and computer science part, and Jonathan was more in the numerical part. And in this method, we have a polynomial system, and this system is given over rationals. And this is mostly because the coefficients are floating point numbers, so just we convert them to the rationals. But here, our assumption at this, the given system is the system we know. We don't really consider the errors in the given systems, because in the one of the reasons we use to convince other people is that robotic algorithm, models, because in the robotic models, what they have the ratios are exact. They are coming from some trigonometrical functions, whatever. So what we work on is the rationals, and our assumption is the ideal is zero dimensional. So we certify the approximate real roots of polynomial systems. Also, it works on just real roots. Another reason is only when you solve polynomial systems or any kind of differential system, the only real roots have the application in the real world. In the complex roots are just complementary in the mathematics part. So real roots are actually ones they are interested in, the real points. So this is why we were just focused on, after the previous project, we were like, okay, they're just interested in real roots, so why we just don't focus on real roots? And then we came up with a completely different approach. And yeah, this is completely different, independent from the alpha theory and Newton method. We don't need the convergence of Newton method, and it works in some systems when alpha theory doesn't work. So this is the very summary of our steps, and I will explain how we actually use each step. So first, we are given the system. We use a numerical system and get the approximate roots. When I listed the software I used, the Bertini was one of them. So Bertini is a tool. It's actually a homotopy continuation method. This is very homotopy based approach with some numerical senses. So it's a very one of the biggest application of symbolic numerical computation also. So you give that your polynomial system to the Bertini, and Bertini gives your solutions, and it's quite in theory it's a quite reliable method, but the results, the solutions are not certified. So this can be like an extension to that system, so you can actually certify your results. And so in the first step, we use Bertini and get approximate solutions of the system. And but of course, we were interested in real ones to certify. Then we construct an approximate Hermite matrix. I will define what is Hermite matrix. It's not a Hermitian matrix. It can be Hermitian, but it's not the Hermitian we know. It's coming from Hermite's work from 1853. So that specific matrix is actually extracted from a letter from Hermite to Sturm. So Sturm and Hermite were writing letters to each other back to back, and in 2 or 3 letters, after later years, they start to construct this kind of matrix. And now this, even though it was constructed by using complex numbers, because all the writings are on complex numbers, and very interestingly, what they ended up is a different kind of real matrix. And so after we construct that kind of matrix, for the entries, we use that approximate root. So all entries are floating point numbers. What we do is we use some methods to rationalize each entry. Okay, we constructed a matrix. All the entries are floating point. Then we turn it to a rational one. And what we have is it's just a matrix that we don't know. So we need to actually first make sure that that rationalized matrix is the real Hermite matrix. Because we don't know the roots. We didn't use the exact roots, right? So then in here, we certify the matrix itself. And once we have the exact matrix, we don't know the roots, we didn't use the roots, but we still have the matrix is based on the exact roots. And we compute the signature. I will remind you of signature. And then we use the certification theorem. This is a very actually simple theorem that I will show you. Using that theorem, we can understand if that is really the good approximation or not. So we can certify the approximation. So let me define the Hermite matrix. Now, as I said, this definition is coming from the letters from Hermite and Sturm, but Hermite was constructing the matrix. So for some other actually very interesting purposes. So the matrix can be defined based on Wander-Wander matrix. So I worked on Wander-Wander matrix a lot. This is why yesterday I was trying to figure out that was very different kind of Wander-Wander matrix, and it's a really amazing matrix, and it can pop up in different areas of mathematics. So we work on a Wander-Wander matrix. Okay, I will tell you how we define it. And the transpose of that times a diagonal matrix, this G is a diagonal, a specific diagonal matrix, and times the Mondai matrix itself. So it's just a multiplication of three different matrices. Okay, this is okay. And then in the other definition, we actually it's based on a trace of a different kind of matrix. This is a multiplicative matrix. So this is a different kind of matrix. You can define it in a different way, and you get the trace, and you end up with the same matrix. They're equivalent, and their equivalency is like whole chapter in a real algebraic geometry book. But they're equivalent, I assure you. And we extended matrix a little bit with the order basis just for our purpose. We didn't have that definition at the very beginning, but we needed that when we start constructing the algorithm. Because when we try to do the stuff in the algorithm part, we figured that we need something bigger than that, and we found a way to extend the matrix in a specific way so we can use it in the algorithm. So these are these two examples. This example is just showing you how actually that matrix is a well-behaved, very well-constructed, structured matrix. Okay. At the end, the computations are kind of ugly, but at the end, you end up with this kind of matrix. It's a Hanka matrix. Okay. So, so there are some pros and cons of two different definitions, because we use them exchangeable. So we actually took advantage of two different, very different definitions of the same matrix in the algorithm. So, and a signature is the just number of positive eigenvalues of a matrix. It's just if it's a real and symmetric matrix, which is real and symmetric, by the way. So and the minus negative eigenvalues of x. So this is the signature. And in the theorem, the Hermit himself's theorem says the signature of that specific Hermit matrix tells us something else. The signature of a Hermit matrix is actually the number of real roots. That root makes G positive, and G is called an auxiliary polynomial here. So Hermit matrix, every single Hermit matrix is based on some given ideal and an auxiliary polynomial. That auxiliary polynomial has a really interesting role. So the number of real roots that makes the polynomial, that auxiliary polynomial positive, minus the number of real roots that those numbers makes the that auxiliary polynomial negative. And in the case of 1, if we pick the G as 1 as a constant function, then the signature of the Hermit matrix actually gives us the number of real roots. So in the multivariate case, it's not that obvious to find the number of real roots, but this is a really nice tool. This is not always usable, but when you can use it, it's a really like simple tool, and the computation-wise, it's really cheap. And how we define G? Okay, in our purposes, for our root certification purposes, we define G in a specific way. So how we define is, so if we are interested in this neighborhood, okay, if we are trying to figure out if there's a root here in a very, very small neighborhood, we can define epsilon to be really, really small, because if this number is good enough for application, if it can be certified, then we can define that little neighborhood. Or you can be interested in if there is no root around, you can also certify that. Okay, if there's a root or there is no root. So we define G using the definition of that open ball. Okay, so if the z x minus z squared minus epsilon squared, so we can have a nice little auxiliary polynomial. And in the theorem, this is the main theorem we use, and this is the last thing I will mention here, is the signature of that Hg should be equal to signature of H1. So it means that this is true if and only if there is no real root within the closed ball in the radius of epsilon around the star. So what I mean here is if the signatures are the same with G. So I define G to be the open ball around that Z star, right? And H1 is giving the number of all real roots. So if there's any, if they are equal, if the signatures are equal, and it means there's no real root in that neighborhood. So at least one of them should be in the open ball of the neighborhood. So this theorem, also proof is not complicated, but this theorem gave us all the tools to construct everything. So based on this and based on this, okay, and then we use that theorem. We compute that and construct the matrix, and we rationalize the numbers. We use continuity diffractions and stuff, and then we certify. These are all different algorithms. So for each step, we constructed new algorithms, and at the end, what we use is the theorem, the certification theorem I just quoted. So this is all I want to do today.
Thank you very much. Questions? Yes, please.
So I assume if you have just a polynomial, and I give you a univariate polynomial and an interval, and I want to know two things. No zeros. Can you check it? I assume
Yes.
this will show.
Also, we can
Up to
check
which degree? It's in a reasonable time.
No, I mean, I don't know for univariate, but that should be higher. But by 70 to the degree 70 with 50 variables is now can be done.
So this univariate should be very high.
Yes,
So,
I think so. I mean, I didn't even consider univariate because Sturm theorem can do that. So Sturm method can do that.
Whatever is the method.
Yeah.
But now my question is, the next question is, if I give you again this univariate and again an interval, what with parameters?
Yes, that would be tricky. That would need some modification in the method, but that can be possible. I don't know.
So
it depends what kind of parameters.
Well, I have real parameter, let's say one, which is positive. And I want to prove that this polynomial has no zeros in this interval for all positive, let's say one parameter, or two parameters, or maybe 10. So, can you do this? Or sometimes I want to prove there is exactly one root.
There's exactly one root is one of the examples actually I ran in my code. It worked, but I don't know about the parameter. I have never worked with parameter, but I think that can be possible.
In most cases, at least one parameter is what you want. Without parameters, sometimes also without parameters, but in most cases.
And right now, actually, the project or the paper I'm working on is on the eigenvalue certification. So, because the eigenvalue is a univariate case, kind of. So I'm working on univariate. And in univariate case, actually, there are some interesting properties I'm just discovering. Very interesting properties. Somehow it's easier, but in some cases it can be even harder. That's also some struggles I'm working on. So I'm just trying to certify that in some areas there are some, I'm just trying to certify some spectrum and stuff.
And so you have already some algorithm?
Yeah,
usable software?
The rest of the thing was actually the algorithm, but I just...
No, I mean usable software, download and use.
I have my code, but I don't have that. But I mean the code is an algorithm looks like this. So in each step you just
But of course I will not program this stuff. So
Needs a software.
Download something.
Yeah. In Maple in Sage I have two different implementations.
But it's not an open or something.
No, not really. But if you are interested in a specific thing, I can modify my code and. Right now I'm using it in Sage, so.
Thanks.
So maybe you said this and I missed it, but your polynomials, they are with coefficients over a field. You're using symbolic computation with the coefficients like you want exactness, or it's more like if it's a real polynomial, so complex polynomial, what kind you use to have the coefficients?
I use the on ratio polynomials. So they're all on ratios.
Okay.
We ended up in rational because we were working on floating points. Floating points are basically decimals, and you can write them as a ratio, and you can use it as a rational input. So this is how we use many things.
Okay, because I think in previous, like in the beginning, you were saying about methods, and they were like real polynomials for other methods.
Yeah. The other method, if you have a constraint system, you can use reals. You can also certify context rules.
Okay. And then.
But it doesn't work when Newton method is not converging.
Okay.
But it's usually very useful.
Okay.
Good. Some other questions? Okay, thank the speaker again. And we have a small coffee break now.
Okay, thank you very much. I would like to thank the organizers for the invitation to give a talk on this nice conference. And I also want to thank all of you for coming on the last day of the conference here. So I'm very happy to see you all here. And the topic of my talk is from algebra and representation theory, and more precisely representation theory of the group GLN. So on the first day we heard a very nice talk about the symmetric group. Now we'll talk about GLN. There are a lot of similarities, and we'll see some of the similarities. We might comment on the similarities if we have time, but some of the definitions will be the same and we will repeat them. And yeah, we're going to introduce the main definitions so that I hope at least in the beginning you can follow the talk even if you're not from this field. And the other field is not only representation theory, it's also this part here, relatively free algebras, which comes from algebras with polynomial identities, and we're going to define them. And we'll see how we can use representation theory to study this kind of objects. Okay, so let me first fix the notations and start with some basic definitions. So we work over a field of characteristic 0, and we fix V to be a finite dimensional vector space over our field K with a fixed basis xn. And by K of xn, we'll denote the free associative algebra generated by this set, which means all non-commutative polynomials in these variables. So the vector space spanned by all non-commutative monomials in these variables. And another way to look at this object is as the tensor algebra of the vector space V. Okay, and then we start with the first definition. We say that an associative unit of K algebra A satisfies a polynomial identity in n variables if there is some non-commutative polynomial from K of xn, such that if we replace the variables with arbitrary elements from the algebra A, we get 0. So all the elements of the algebra, they satisfy this polynomial. And if we have such a polynomial identity, if A satisfies such a polynomial identity, then A is called a PI algebra. And we have some starting examples. So if we have a commutative algebra, then all the elements inside commute, so they satisfy this commutator identity. So commutative algebras, they are algebras with polynomial identities. If we take then another example, the exterior algebra of any vector space, then it is not difficult to see that all the elements satisfy a triple commutator identity, where we define a triple commutator in this way. So we take the normal commutator of the first two variables, and then again the commutator of the result with the next variable. And also it is also not difficult to show that every finite dimensional associative algebra is also a PI algebra. So PI algebras somehow are considered to be generalizations of both commutative and finite dimensional algebras. Okay, then the next definition that we need will be the notion of a T ideal. So T ideal in K of xn is any ideal that is closed under all K algebra endomorphisms of Kxn, which means that if we take an element from the ideal, so non-commutative polynomial, and if we replace the variables with arbitrary elements, we again obtain an element from the T ideal. And we'll give examples on the next slide. And then why do we need the notion of T ideal is because if we take the set of all polynomial identities of a PI algebra A in n variables or less, then we get a T ideal in K of xn. And conversely, every T ideal is actually the T ideal of identity satisfied by some PI algebra. So that's why we need the notion. So T ideals are some special ideals inside K of xn. And here are some examples. So we already defined the double and triple commutator. In the same way, we can define a commutator of length p, which will be iteratively defined using this formula. And then the ideal generated by all commutators of a fixed length will be denoted by IP, and this is an example of a T-ideal. So it is closed under all K-algebra isomorphisms. And in this way we get a chain of ideals. So the ideal generated, the usual normal ideal generated by double commutators. Then inside is the ideal generated by triple commutators, and so on. We get this chain of ideals. And then the main object of interest in this talk will be the quotient algebra of K of xn mod a T-ideal. It is called the relatively free algebra of rank n. And why is it called like this? It's because if we take all PI algebras that satisfy the identities from I, then K of xn will be the free object in this set. That's why it's called relatively free algebra. And the starting example is if we take K of xn mod the ideal generated by double commutators. This is the well-known symmetric algebra of vector space V, and this is the free object in the set of all commutative algebras. Okay, and now as we said, we need to introduce some representation theory in this setting. So this is enough about definitions about relatively free algebras and algebras with polynomial identities. Now we introduce an action of the group GLN in this setting. So first, since we have a fixed basis in P, we have the natural action of the group GLN on P by matrix vector multiplication. That is well known from linear algebra. And with this action, V becomes a module over GLN, which means just a vector space with a linear action of the group GLN, invertible linear action. Module and representation we'll use interchangeably in this talk. So V is a modular representation of GLN because GLN acts very naturally on it, and it is called the natural representation usually, or the standard representation. And then we can extend this action to an action on the whole K of xn in this diagonal way. So we take a monomial, and how do we act on the monomial? We act on each of the variables separately. And and then we extend by linearity to the whole algebra K of xn. So this is again a very natural action, and in this way a K of xn is also a representation of GLN, but now infinite dimensional. And so in this action is also extended to the quotient because all these T ideals, they are GLN invariant, and that's why the action on K of xn is inherited by this quotient. And one of the important questions in the theory of PI algebras is to describe this quotient, so the relatively free algebra, as a module over GLN, which means to decompose it as a direct sum of irreducible GLN modules. And let me recall, so on Monday we heard what an irreducible module or irreducible representation is. This is just a representation that doesn't have sub-representations. And so we want to decompose this into the irreducible pieces as GLN module for different classes of T ideals I. And okay, so this question is important in PI theory, but there is also another motivation to study it. It comes from invariant theory, because we would like, when we will talk about this later in the talk, but let me mention that if we know this decomposition, then we can compute degree bounds of generators in such kind of algebras of invariance. So there is also motivation to study this question coming from invariant theory. And in this talk, we'll consider two classes of T ideals. That would be ideals generated by long commutators and ideals and products of such ideals. Okay, and since we want to describe the structure of the GLN module, let us recall how we can actually index or how we can identify GLN modules. So this is again a recall from basic representation theory. We start with a partition, which is just a weakly decreasing sequence of numbers. Here n will be important because this is the GLN, the n is the GLN. So we'll look for partitions with n parts. And we recall that at each partition we can associate a Young diagram, which is a diagram of boxes, such that on the first row we have 1 to 1 boxes, on the second row we have 1 to 2 boxes, and so on. On the last row, on the nth row, we have 1 to n boxes. So to each partition we associate, we can visualize it in this way. And there is a standard fact from the representation theory of GLN that all irreducible submodules, GLN submodules of K of Xn, they are indexed by such partitions with n parts. And by v lambda, we will denote the irreducible module that corresponds to the partition lambda. This is exactly like in the representation theory of Sn. Their irreducible pieces are also S, let's say not Sn, but Sd, for example, the symmetric group of d variables. Again, it is irreducible representation are indexed by partitions, but there it was important what number we partition. And now the important thing is not the sum of the parts, but that they are n parts. I mean, it could be zeros in the end, but we cannot have more than n parts in order to have a GLN module. I mean, if we have GLN plus 1 module, then of course we'll get partitions with n plus 1 parts. Okay, and very basic examples of irreducible modules. As we already mentioned, the vector space V is an irreducible module, and it corresponds to the partition lambda that has 1 in the first position and zeros after that. Then if we take the ith symmetric power of V, this will be again an irreducible GLN module, and the partition is this one for each I. And for the jth exterior power, this is again an irreducible GLN module. This is the partition with j ones here in the beginning and then zeros. Okay, these are some examples of irreducible GLN modules. So let us now go back to our problem. We want to describe this decomposition. So K of Xn, how do we decompose the K of Xn mod I? How do we decompose it as a direct sum of irreducible GLN modules? Or in other words, what are the multiplicities here? In this, these are some numbers, they could be 0 or positive, and what are these multiplicities? And let us describe first what is known for the ideals that we are interested in. I mean, there are other T ideals, but the ones we are interested in, we'll describe now the known results. So if we have an ideal generated by a long commutator, by long commutators, then these multiplicities are known in the cases when P is 1, 2, 3, or 4. And the first three cases I have given here. So if we take K of Xn mod the ideal generated by double commutators, as we said, this is the symmetric algebra, which is the direct sum of all symmetric powers of V. And as we said on the previous slide, they are already reducible GLN modules, and each of them is described by such a Young diagram. So we have I in the first row and zeros after that, so nothing in the next rows. So this is the decomposition, the very classical example. And then this is also considered to be a classical example in the theory of algebras with polynomial identities. We take K of Xn mod the ideal generated by triple commutators, and the decomposition is given by Hook diagrams of this form, where the first row can again grow arbitrarily large. And one more case we are going to give as an example. This is when we quotient by the ideal generated by commutators of length 4. This is one concise way to write down the decomposition, so it gets more and more complicated. In this case, we are not going to write on a slide because it's already too complicated, but it's known. The composition is known, and this is about one ideal generated, one copy of the ideal generated by commutators. Now, if we take products, there are also some known results. If we take a product of two such ideals, the results are known in the cases when the product is of two copies of the ideals generated by double commutators. Then these cases, two cases are known, and they are done by Centrone, and the first one by Mishchenko, Regev, and Zaitsev. And what is also known, or at least partially known, and there are explicit multiplicities for one partitions, if we take k copies of I2 for arbitrary k. This case was also studied, and this case when we take k copies of I3, this case also has some known results, and we'll hear more about this probably in the next talk, but maybe from the point of view of the symmetric group again, not of GLA like in our talk. Okay, so these are explicit results, and there are also some bounds that are known. And the first one is a classical theorem of Mitsuru and Regev, which says that if we write down like this the decomposition of k of x mod I, then the non-zero multiplicities are supported in full diagrams of this form, which means that for the first k rows, we don't know anything about the partition, we have no bound, but from the k plus first row on, the number of boxes in the corresponding row is bounded by the number L. So this is bound on the non-zero multiplicities, and that bound was improved then by Barrow in 2005, saying that all non-zero multiplicities, they are supported in diagrams of this form, where that means that the first omega 0 rows of the partition, they can grow arbitrarily large. The first omega 1 columns, they can also grow up to n. And the other parts, they are bounded in this rectangle for some numbers S1 and S2. Okay, and also Barrow computed these numbers, these two numbers in some cases, and I have given them. So when we take the ideal I to be ideal generated by non-commutators where P is greater than 2, then omega 0 and omega 1 are equal to 1. They are actually called the arm of the partition and the leg of the partition, and this is the arm length and the width, the arm width and the leg width of the partition. So he computed them to be ones in the case, in this case, and when we take k copies, he showed that they are both equal to k. And similar results for the k copies of I2 with a bit more complicated expression, but still explicit one. And the first thing that we can say about, we can add as an information to this thing is that we, for the same ideals, we compute this number as 2. And we give a sharp bound on the number as 2. So let us see to be equal to p minus 1. So let us see how that goes. We introduce some more notations now. So we take a commutator, we call commutator pure if only basis elements appear inside. So we don't have products of basis elements or other monomials, just a commutator of basis elements. And these are pure commutators, and Bn will denote the subalgebra generated by pure commutators. And the elements of Bn, they are called proper polynomials. And if we consider the natural projection from K of xn to K of xn mod I, by phi I of bn will denote the image of bn, so that would be the subalgebra of proper polynomials inside the quotient. And in the case when the ideal I is just ip plus 1, we'll denote this projection by phi p. By phi p. And there is a theorem of Drensky that relates why is this subalgebra Bn important. This theorem says that as GLN modules, K of xn mod I is isomorphic to the tensor product of the subalgebra of proper polynomials and the symmetric algebra. So we can reduce the problem of studying the GLN structure of this thing to the problem of studying the GLN module structure of this simpler object. And so this is the first thing we do. And that's the first result, that if we write down the decomposition of this thing, then vector space V lambda, GLN module V lambda appears with non-zero multiplicity in this decomposition. If it appears with non-zero multiplicity, then necessarily lambda 1 should be bounded by the number of b minus 1, which in particular means that this algebra is finite dimensional, because there are only finitely many partitions that have this bound. And also this bound is sharp. We always can produce in the decomposition a partition which appears with non-zero multiplicity and has lambda 1 equal to b minus 1. Let me very quickly say what kind of methods we use for the proof. I will not go, it's not difficult proof, but I'll just mention the ideas. So the first idea is this observation that if we write down the weight space decomposition of this space as a GLN module, then all the weight spaces, they are given by integers, n-triples of integers. And the vectors that, the weight vectors that correspond to the weight mu, they are exactly sums of products of pure commutators, such that the variable xi appears in each product mu I times. So this is not a difficult observation, but what it tells us is that if we want to write a bound on lambda 1, it's enough to estimate how many times x1 can appear in a product of pure commutators. So give a bound on the number of times the variable x1 can appear in such a product. And for such bounds, we can use theorems on products of commutators. And here I have listed the theorems that are important, results, and then of course they can be iterated for many products. I have not given iterated versions because these are enough. So if we take two ideals generated by long commutators, the interesting fact is that if we multiply these ideals, the result will land in another ideal generated by long commutators. And for arbitrary integers, this is the ideal that we go to. But if one of the integers is odd, then we have a better somehow bound, because this ideal is smaller, right? You remember that we had a chain of ideals in the beginning, and the bigger the number here, the smaller the ideal. And so if one of the numbers is odd, then this product goes into a smaller ideal. And this unfortunately does not hold if we drop the condition on m of 1 or n2 being odd, but there is one more condition that we can add to make this bound again work. So if we take two commutators that are even commutators, so they don't satisfy this bound, this condition here, but the last entry is the same, then we go to the smaller ideal. And so these three things and their iterated versions give us the bound on the partition that can appear with non-zero multiplicity. And based on this, so this was the bound for the subalgebra of proper polynomials. And now we recall the theorem of Drensky here. And now with standard methods from a representation theory, how we multiply, how we take tensor product, when we have a tensor product of several representations, how we decompose this tensor product. The general rule is the little Richardson rule, but in this particular case, since one of the constituents here in the tensor product is simple representation, I mean, the symmetric algebra is considered to be well known and simple, so in this case, the Pierre rule, which is a special case of little Richardson rule, can be used. So when we use such rules for decomposing tensor products, we obtain as an immediate corollary the restriction on the non-zero multiplicities for the whole quotient algebra, KLXN, mod IP plus 1. And the restriction is that if we have a non-zero multiplicity here, then lambda 1, we have no, it can grow, we have no restrictions on lambda 1, but then lambda 2 has to be less or equal to p minus 1. And again, this bound is sharp. And we can see it in two examples in which we know the decomposition. So when we take this algebra, we know the decomposition, and what in this case, p will be equal to 1. So the bound will be 0 on lambda 2, and this is exactly what happens. We have the first row of the Young diagram can grow arbitrarily large, but we have nothing below. So the bound is obtained. And also in this case, then p will be 2 in this case, and so lambda 2 will be bounded by 1. And that's exactly what happens. The first row grows, but we can have only one box after the first row. And this bound is also exact for the other cases. Okay, and there's another corollary of this result when we take a product of several copies of such ideals using the previous results and some methods how to relate this algebra when this is a product to the other algebra give us the result in this case, which says that we have non-zero multiplicities in the decomposition. If we have a non-zero multiplicity in the decomposition, then we have no restrictions on the first k rows of the Young diagram, and then for the k plus first row, we have this restriction, and for the 2k row, we have this restriction on the Young diagram. And okay, let me now go to applications. As I mentioned in the beginning, there are applications in invariant theory. So let me first recall what the topic of classical invariant theory is, and then we'll go to non-commutative invariant theory. So classical invariant theory investigates the properties of this algebra of invariance, where G is some subgroup of GLN. So algebra of invariance usually means that we take all these elements from the symmetric algebra of B, which stay fixed under the action of all elements of G. So they are invariant under the action. And classical invariant theory asks many questions about the properties of this algebra. And for example, one important question is when is this algebra finitely generated? And here we have Noether's theorem, which says that this algebra of invariance is finitely generated for every finite subgroup of G. There is even a bound, Noether's bound, on the number of on the degree of the generators. Then we have Hilbert's theorem that says that this algebra of invariance is finitely generated for every reductive subgroup for GLN, and there is also a theorem that for every maximal unipotent subgroup of a reductive subgroup, again we get the finitely generated algebra of invariance. And now one way to do so this is all classical and all very known. Of course, there are some other questions that are not known, but we'll focus on this question about finite generatedness. And one way to do non-commutative invariant theory is to replace S of B with with the quotient KMXN mod I for TADO I, and then I investigate the properties of this algebra of invariance for different classes of groups. And then Domokos and Rensky, they prove a version of Hilbert's theorem in this setting, which says that if we take the TADO I to be generated by long commutators, then this algebra of invariance is finally generated for any reductive subgroup of GON and also for any maximal unipotent subgroup of a reductive subgroup. And this is almost an if and only if situation, so if we take here another TADO, then that will not hold. Okay, and what we want to do in our talk is, as an application of the previous result, is to take G to be one of these groups. The first four of them, they are reductive. And the last one, this is the group of upper triangular matrices with ones on the diagonals. So this is a maximal unipotent subgroup of GON. And for these groups, we would like, since we know that the algebra of invariance is finitely generated, we would like to give upper bounds on the degrees of generators. And these degrees of upper bounds, they are denoted by beta usually in invariant theory. So this beta will be the upper bound of a degree of the maximum degree of a generator, of a homogeneous generator of this algebra of invariance. So they are generated by some non-commutative polynomials, and we give a bound on the degree of this polynomial. And here we're going to use Hilbert series. So I recall also the definition of the Hilbert series. So for any finitely generated graded algebra, in our case this will be non-commutative polynomials here of degree I. So this is the grading comes from the degrees of the polynomials. So for any such algebra, the Hilbert series is this formal power series where we take the dimensions of all these components and multiply them by t to the power I. And here, since I would like to mention here, since the first talk was about symbolic computation, is that sometimes we use symbolic computations to compute this Hilbert series for small degrees of the algebra A. And yeah, so we need symbolic, not numerical computation, because the result has to be a rational function, not a number. So we also use in our work symbolic computations, but not in this talk. Here we'll do some bounds, and these bounds will be obtained theoretically. So how do we use the Hilbert series in order to do what we want, to give some degree bounds? This is one theorem that we will use in the case is SLN or UTN, which says that if A is any finitely generated graded algebra over K, which also is a GLN module, and if we know the decomposition of A as a GLN module, then the Hilbert series of the algebra of invariance, where G is one of these two groups, is given by this formula. The multiplicities here and here are the same, but now this is not over all partitions lambda, it's only over some partitions lambda, and in the case of SLN, we take partitions with equal entries, and in the case of UTN, we take all partitions. So if we know that the composition is a GLN module, we can compute the Hilbert series. And our first part of the talk was exactly about the composition as a GLN module. So we gave some bounds there on the non-zero multiplicities, and now we can use these bounds to get not exact formula for the Hilbert series, but bounds on the Hilbert series, on the form of the Hilbert series. And this is the first result. So if we take SLN, the group to be SLN, then this formal power series is actually a polynomial, it's not infinite sum. And we give a bound on the degree of this polynomial. This is the bound we get. So in particular, this means that this algebra of invariance is not only finitely generated, but but also finite dimensional. And when we compute the degree bound, we actually compute not only the degree bound of a generator, but of any homogeneous element. And this is the degree bound in this case. And for SLM, there is actually a stronger theorem or corollary, because which holds for any TIDL I. So for any TIDL I, we can say when the algebra of invariance is finite dimensional based on these four numbers that appeared before in Berer's theorem. If you remember, this was the arm of the partition, this was the leg of the partition, and these two integers gave the dimensions of the rectangle in the middle. And so the statement is that for any TIDL, if n is greater than omega 0, then the algebra of SLM invariance is finite dimensional. And for the Hilbert series, we get an explicit bound on the degree. So it's a polynomial, and this is the bound on the degree, n times s2. And further, if n is greater than s1, we get an even better bound on the degree. It's again finite dimensional, and we get a better bound on the degree. So for SLN, we actually have result not only for ideals generated by long commutators, but for arbitrary ideals I. Okay, now let's go to the other group that we mentioned, the group of upper triangular matrices with ones. On the diagonal here, the Hilbert series is not a polynomial, it's a rational function. And we can, where this is a polynomial in the numerator, and the denominator is has a very easy form. And we can, based on our bounds on the GLN module decomposition, we can bound the degree of this polynomial in the numerator. So this is a bound on the degree. And based on this form of the Hilbert series, we obtain that the maximal degree of a generator of our algebra of invariance is bounded in this way. So when p is greater than 1, it is n times p minus 1, and it's 1 in the case when p is 1. Okay, and then we have similar approach for the case where we consider the two orthogonal groups and the symplectic group. But now, so we have a joint result with Drensky that has a similar form to the previous one for GLN, for SLN, and the UTN, which says that if we know the decomposition of our starting algebra as a GLN module, then for the algebra of G invariance, we get this form of the Hilbert series with, of course, some constraints on the sum, on the lambdas that can appear in the sum. And for when G is the group SP, this sum will be only over partitions where the first two rows have the same number of boxes, and so on. The second two rows also, and so on. And when G is the group ON, the sum is over even partitions only. And for SON, we get even or odd partitions. And here the difference is that to make this theorem work, now we have to restrict ourselves to the field C. So this result is over C, not over arbitrary field of characteristic 0. And why? There is what is the main ingredient in this? It is a classical theorem that says for a GLN module V lambda, what is the dimension of the subspace of SP, for example, invariance inside. And this is a classical theorem which says that V lambda has a one-dimensional SP invariant subspace if and only if this condition on lambda holds. And that is why this condition appears here. And this theorem is over C, so that's why we restrict ourselves to C. So from in the next slides, we'll consider only algebras over C. And so let us now use this theorem to obtain degree bounds for the three groups. Now the results will be similar to before. In the case of SP, we get that the Hilbert series is again a polynomial. So this algebra of invariance is again finite dimensional, and this is the degree, the bound on the degree of the Hilbert series that we obtain. And also then as an immediate corollary, we get a bound on the maximal degree of any homogeneous element of this algebra of invariance. Then in the cases of SON and ON, the Hilbert series is a rational function, and we get again a simple denominator and some polynomial in the numerator, which we don't know how it looks like, but we can bound the degree of this polynomial, and for ON this is the bound here, and for SON this is the bound on the degree of the polynomial. And based on that, we can obtain as a corollary bound on the maximal degree of generator in the case of ON and SON. Another question that comes to mind is to what extent these bounds are exact. Can we check how far they are from being sharp? So do we have really a generator, for example, with this degree? And we can check this in the case p equal to 2. So let us see how this goes. So when p is equal to 2, the above bounds, they give n for these groups, and 2 for in the case of ON. And we also, in a joint work with Brensky, we have computed explicit generating sets in this case. So we can check whether this bound is obtained or not. And I have given here the generating sets because they are not difficult. So in the case of the algebra of SLN invariance, this algebra is generated by just one polynomial. This is the standard polynomial for degree n. So this is a polynomial of degree n, and therefore the bound n is obtained in this case. If we take the algebra of UTN invariance, it has many generators, so it is generated by the polynomial x1 and by all standard polynomials of degree d. So where d can go to n. So we again have a generator of degree n. In this case, so again the bound is obtained. And now on the three other cases. So when we take the algebra of SP2S invariance, we have again one generated, which is of degree 2. And the bound we have is n. So in this case, the bound is not obtained. And for ON, we have again one generator of degree 2. And here we see that the bound is 2 in this case, so the bound is obtained. And finally, when we take the SON invariance, there are two generators, one of degree 2 and one of degree n. And so again, the bound is obtained. So the result of this checking is that when p is equal to 2, so when we quotient by the ideal generated by triple commutators, this bound is sharp in all cases except when G is the symplectic group. When we take p equal to 1, so the previous one, I didn't mention it because this is the symmetric group and it's very classical. There all bounds are obtained. So for p equal to 1, all bounds are obtained. For p equal to 2, already 1 is not obtained, and our actually expectations are that the higher we go, the further away will be our bounds from the exact maximal degree of the generator. So these bounds can be improved this is our expectation. We don't know because we don't have explicit generators, but our expectations are that these bounds can be improved when p grows. Okay, yeah, that would be the end of my talk, so thank you very much for your attention.
Questions? Do you have any questions?
Yes?
So these restrictions you get in the condition when you have this partition partitions where the number of columns of the Young diagram is they were bounded by something.
Yes.
Well, I've seen a similar thing with the so-called temporally live algebras, where you get that you don't
Which algebra?
temporally live algebras, which have well, we're talking about finite partitions then, so you don't have this that you can have not as many parts as you want, but you have the maximum number of columns has to be 2. So I was wondering, probably you've never heard of these algebras, but whether there is a connection or there is something between the two.
But you should recall what is temporary algebra, leaf algebra. So these are some kind of commutators, but specific commutators, not all.
Okay, they are not associative algebras.
So the temporary algebra, there are many ways to define. One is as a quotient of the Hecke algebra that I talked about. So the Hecke algebra will have all partitions of n,
Okay.
and then when you quotient out, you get that only the ones that have at most 2 columns give you. So I saw this and it reminded me that maybe there is something there, that this algebra that you get and you have a parameterization, maybe they are connected.
I don't know, maybe that would be interesting.
And anyway, to quotients of the
Yes,
Hecke
yes.
algebra or the symmetric group algebra, because you can see it there too.
Okay,
The
but-
symmetric group and quotient out and get this restriction to the number of columns.
But there, do we talk about representations of the symmetric group or the GLN group?
No, not GLN, not GLN. It's more connected to the symmetric
I see,
group, so
I see,
it's on
yeah.
that side.
Yeah.
But you also get restriction on the number of columns.
Yeah, that's interesting. I will look into that. I don't know. Maybe there is a connection. Yeah,
Yeah.
because again here, if we take just KLXN, there are no restrictions. And then when you quotient, you get restrictions. Just exactly what you
Yes.
said there.
Yeah.
And when you take the Hecke algebra, no restrictions, and then you quotient, and then you get multiple columns. I don't know. Maybe that would be interesting to investigate. I don't know. But yeah, thank you for the remark.
Okay, I have
Yes.
In fact, I have two, but not very many, not very professional questions. One is, have you studied a connection between the algebraic properties of the algebra itself, the free, relatively free algebra, and the invariant algebra? Have you ever studied some kind of correlation? Or at least one algebraic property which has implication on the algebraic property of the invariant algebra? First question. And second, very simple and possibly very naive, how are the Hilbert series of a relatively free algebra related to the Hilbert series? Is there any relation at all to the Hilbert series of the corresponding invariant?
Yeah, the second question I can answer. The first one, I mean, this is the algebra of invariance is a subalgebra here, but depending on the group, I don't think there is a relation. Depending on the group,
Some
it can
kind
be
of
very different.
homological characteristic of the invariant algebra?
It cannot be done for any group. I mean, for particular
No,
group,
I
maybe
don't think
there
there
are
are even
relations.
even one type of group. Even with small n, anything, just something.
From the Hilbert series, we can get there.
Get
Let me
the
go
graph,
to the
get the graph.
Yeah, this is exactly the connection. I mean, this decomposition, it can also be written in terms of the Hilbert series of the algebra A. And so we see that the multiplicities that appear in the Hilbert series of the algebra A, the same multiplicities that appear in the Hilbert series of the algebra of invariants, but with some restrictions on lambda. And these restrictions depend on the group G. And we know these restrictions for these 5 groups that I mentioned. It would be nice to... Yeah, it would be nice to know them for more. And this is also not only for relatively free algebra. This is here a more general setting for any algebra that is graded and is also a GLN module. There is this relation between the Hilbert series of A and the Hilbert series of the algebra of invariants. So we can say from there a lot about this Hilbert series. for these 5 groups. Yeah, for other groups, I don't know.
This is already very.
Okay.
Just check my understanding.
Okay.
At the beginning, you mentioned each Young diagram lambda gives a irreducible representation.
Yes.
So is the representation just generated by x1 to the power lambda 1 times x2 to the power lambda 2?
Yes, in k of xn, in k of xn exactly. K of xn, the whole free associative algebra. Then each representation there is generated by this monomial. Yes, and then when you go to the quotient, you get a linear combination of these monomials. Not only because the monomial itself might not be in the quotient, but some linear combination of monomials with the same degree. So yeah, that's why it's not just one monomial, but some linear combination of monomials with the same degree will generate the corresponding representation in the quotient. Yes.
Okay, thanks. Another question. So Hilbert theorem tells us the G invariant algebra is finitely generated. So in that's the case, I equal to I2, right?
Yes. The case I equal to yes, exactly. Here, the symmetric algebra is exactly when I is equal to I2. Yes.
Okay. So in general, do we know the G invariant?
You see here you have 3 parameters. One of them is the group, the other is the TIDO, and the other is the number of the variables.
Okay.
It turns out that if you have the number of the variables is not important. If something holds for 2 variables, it holds for n variables. For example, when you speak about finite generation. If you have cluster groups, for example, you consider all finite groups, all reductive groups, then you have a very strong restriction on the identities. For example, if you have all reductive groups and you want to have the algebra to be finitely generated, the algebra variant, this implies that the algebra should satisfy some one commutator, some of this class. If the algebra doesn't satisfy one commutator, yet the algebra variant is not finitely generated in the general case. Also, you have some other restrictions there. For example, but you have some similarity. For example, the Hilbert theorem says that something is a rational function. Here also you have rational functions, the Hilbert series. Or for example, you have other conditions. You have the Moulin formula for finite groups. The Hilbert series of algebra variant. Here you have some analog of the Moulin formula. So there are some similarities, and there are sometimes they are different.
So basically, the Hilbert theorem will apply to the case.
Sometimes it applies, sometimes it holds, sometimes doesn't.
They generalize it. They don't. They use some similar proof, but the things that are missing from the commutative to the non-commutative case, they have to do by hand. But yeah, this is a generalization of the Hilbert theorem because it applies to all TADLs in this form, so also for I2.
Okay.
Yeah. But the proof is like following the other proof and then filling the holes in the proof that don't hold.
Okay. Thank you.
Okay. Thank you to all the speakers.
next year.
Community field and non-community fields.
So,
Sorry, you can discuss this later.
so okay, hello everyone. First, I want to thank all the organizers for the invitation. It's a pleasure for me to talk here today. So, this talk is about joint work with Lucio Centrone and Veselin Drensky. The paper has several computations, so I think that it's a word a little technical. So I hope that I can give you a general idea about this work. Okay, so we'll start defining some notions about algebras with polynomials identities, and after that I talk about the paper. Okay, so let's start. Okay, let F a field and X a countable set of variables. We consider the free associative algebra over F generated by this set, and we denote with this symbol. Okay, so note that the elements of this algebra are linear combinations of words in this alphabet. Okay, and the elements of this algebra we call it polynomials. So, given A an associative algebra and F a polynomial, we say that F is an identity, is a polynomial identity of A is when you make any substitutions for elements of the algebra A on F, you obtain the zero element of the algebra A. Okay, so using this definition, we know that the trivial polynomial is an identity for any associative algebra. Okay, so we say that A is a algebra with polynomials identities, or a PI algebra when A satisfies a non-trivial polynomial identity. Okay, so the first time that this kind of identities appear was in a paper of them in 1922. This paper was about projective geometry. After that, Wagner studied polynomials identities of the algebra of the matrix of size 2. But in this work, they didn't use the formal concept of polynomial identity. Only in 1948, Kaplansky introduced this concept and proved that any primitive PI algebra has finite dimension. So with this work, the area began to be relevant for the mathematicians. Okay, so examples about PI algebras are the following. So commutative algebras. So if A is a commutative algebra and we consider this polynomial, okay, given by this commutator, when you make the substitution for elements of the algebra, you have that this term and this term are the same because the algebra is commutative. So the product is the same, then this expression is equal to 0. So any commutative algebra is a PI algebra. The second example is about the class of the nilpotence algebra with index less or equal than m. So if A is in this class, you have that any product of n elements are 0. Okay, this implies that this polynomial is an identity for this class. Okay, and the third example is about n to f. Okay, we can prove that this algebra satisfies this polynomial. It's a little more complicated than the previous one, but okay, this is not important in this moment. The last example is about one of the most important objects in our work, or the stereo algebra. And this algebra can be defined in the following way. We consider W an infinite dimensional vector space over F with this basis. So the Grassmann algebra
is the associative algebra over F generated by this set with this relation. So the Grassmann algebra is an associative algebra and is not finite generated. But this algebra is a PI algebra because satisfies this identity. Okay? So given a specific algebra, what can we say about the set of its identities? So the first thing that we can say is that this set has a structure because it's an ideal of the free associative algebra and is invariant on the all endomorphisms of the free associative algebra. So this kind of ideal that has this property of invariance are called T-ideals. Okay, but given a specific P algebra, it's very hard to describe all the identities. This is a very hard problem. Actually, we only know the T-ideal of a few algebras. But when we work in characteristic zero, there are some tools and results that can help us to obtain information about the T-ideal. Okay, so from now on, we consider F a field, but the characteristic zero. Okay, so A algebra and TA, the T-ideal of the identities. Okay, we studied this quotient. Why? Because the dimension of this quotient grows almost exponentially, but the dimension of this intersection, this intersection grows factorially. So it's more efficient to study this space than this. Okay? But one tool for the study of this space is provided by the representation theory for the symmetric group, SMY, because this space is an SN module. In fact, Pn is an SN module when you consider permutations in the variables. Okay, but remember that TA is an T-ideal, so this T-ideal is invariant on the permutation of variables, and this implies that this intersection is an SN module of this space. Then when you make the quotient, of course, this quotient is an SN module too. Okay? So using that, given n greater or equal than 1, the SN character of this space is called the n co-character of the algebra A. Okay? So remember that we are working in characteristic zero. Then every SN representation is completely reducible. And the non-isomorphic representation of the symmetric group are in correspondence, in one-to-one correspondence with the conjugacy class of the symmetric group. But this conjugacy class are described in terms of the partition of n, and the partition of n are described in terms of the ion diagrams. So using that, we can decompose the n co-characters into irreducible co-characters. Okay? Note that these numbers are non-negative integers and are called the multiplicities. But if you know these multiplicities in lambda for each partition lambda, you can know the composition of Pn of A as an SN module. Okay? But the question is, okay, given a specific algebra, how can we calculate these multiplicities and lambda? And this is the question that we solve, but for a very specific algebra. Okay, so let me introduce this algebra. Okay, so in the beginning, I talked about the Grassmann algebra, so we already know that this algebra is a PI algebra. Okay, we are going to consider the algebra of the n times m over triangular matrix. Okay? So the explicit form of these multiplicities, know when k is equal to 1 or k is equal to 2. The first case was done by also also an RHF in this year. And the second case was done by Centrone, Okay, but we don't know anything about the explicit form of the multiplicities n lambda when n is greater than 2. So we want to find a method for any n, okay? We did that, and we found two different ways. Okay, so let me talk about the first method. Okay, so the first method is based in this result of Berial and Vrensky, and this result gives us a relation between co-characters and Hilbert series. Why? Because if you can write, okay, you can compute the Hilbert series of this algebra, and you can write like this summatory. These coefficients match with the multiplicities n lambda for the co-character sequence of the algebra A. So remember that we want to calculate the multiplicities n lambda for UTN of E. So the first step was find an expression for the Hilbert series related of UTN of E. So the first method is based in Hilbert series, short polynomials, and symmetric functions. Okay. So for this, let me fix some notation. Okay. So given D and positive ether, we consider the algebra of the formal Poisson series in these variables. After that, we consider the symmetric, the algebra of the symmetric function, the algebra of the symmetric functions, but note that G can be written in this expression, okay, like a summatory of sure polynomials, okay? So here lambda is a complex number, as lambda is the sure polynomial related to the partition lambda, and lambda in no more than d parts. Okay, so using this decomposition, we can define the multiplicity series of a symmetric function G like that. Okay. There is another way to express this multiplicity series, that is using a chain of variables. Okay, so we use this chain of variables, so the multiplicity series can be written in this form too. Okay, but sometimes when you want to make computations, it's easier use this expression than the previous. Okay, it's only a chain of variables. Okay, character sequence. This is the result of Dresden. Okay, so we can define of natural way the multiplicity series of A like that. Okay, note that if you can calculate this multiplicity series, you can obtain the multiplicities n lambda when lambda is a partition in no more than d parts. So in this moment, we will work with multiplicity series instead Hilbert series. So we need to find a multiplicity series for UTN of E. Okay. So the first step was to find an expression for the Hilbert series of this algebra related to this algebra. So we need three ingredients. The first ingredient is, remember that the ideal of this algebra is generated by this polynomial. But this is equivalent to say that the ideal of UTN is n times the ideal of the Grassmann algebra. Okay? The second ingredient is a result of Fermat that gives us a relation between the Hilbert series of these algebras when the ideal of A is the product of these two ideals. So note that we have this hypothesis by the last slide. Okay? So if we want to know the Hilbert series related of UTN of E, we only need to know the Hilbert series of the Grassmann algebra. Okay? But this result is well known for the mathematicians. Okay? So the Hilbert series of the Grassmann algebra is given by this expression. Okay, then using the theorem, the previous theorem, induction over M, we can calculate the Hilbert series of this algebra. But note that in this expression it's not easy to see the multiplicities n lambda. So we need to find an easy way to write that. Okay? For this reason, we work with multiplicity series. Okay? So we have these equalities. Okay? Note that using these equalities, this expression is the product of these, and we can write the Hilbert series of UTN in terms of sure polynomials. So using these equalities, we define two linear operators. Okay? So the first operator is the operator y. Okay? This operator y is given by this expression. Remember that this product is the sum of the sure polynomials S lambda when the diagram of lambda is an horizontal strip. Okay? And the similar way we define this operator that is given by this expression. But this is equal to the sum of the sure polynomials S lambda when lambda is a vertical strip of even length. Okay? But the action of these operators can be written in terms of this multiplicity series. It's only used a Young rule. Okay? So using these operators and the previous expression for the Hilbert series of UTN of E, we find an expression for the multiplicity series of this algebra. Okay? This is given by this. Note that this multiplicity series is given in terms of the previous operators. Okay? Then using this corollary, again the Young rule, we found a description about the multiplicities L lambda for this algebra. Okay? So this theorem says that if you consider a partition lambda, okay, and this the diagram of lambda is not contained in this cube, then the multiplicity n lambda is equal to 0. So using this result, we have more or less a shape of the partition lambda for the multiplicities different to 0. Okay? And after that, we make some computations about the multiplicities, but we consider d equal to 2. So we only know the multiplicities n lambda when lambda is a partition in no more than 2 parts. Okay, so we follow these steps. So the first step is now the action of this operator that is given by the Young rule, and after that we apply this corollary, and this corollary is the expression to the multiplicity series of UTN of E. Then we change these variables and we obtain n prime. Remember that n prime is the multiplicity series, okay? It's only a chain of variables. And after that we have to write n prime as a power series. And finally we can obtain the multiplicities because the coefficient of this term match with the multiplicities n lambda. Okay, so the first case was the Grassmann algebra, and the multiplicity series of the Grassmann algebra is given by this expression. The second case is UT2 of E, and the multiplicity series is given by this expression. Okay, and after that we have to write this series like a power series, and we found the multiplicities n lambda. Okay, note that these multiplicities match with the result of Olson and Rehef and Centrone But this result is a partial result because we only have the information about the multiplicities in two parts. Okay? Finally, we compute the multiplicity series for this algebra in two variables. Okay? And given by this expression. Then we wrote this multiplicity series like a power series, and we obtain the coefficients, but the coefficients are the multiplicities, so we obtain the explicit form to the multiplicities and lambda for ut3 when lambda is a partition in no more than two parts. So this is an result. Okay, so I want to highlight that this method works for any d. You can choose d equal to 4, 5, the number that you want. But this method has a problem because we are working with a fixed d. This means that this method only gives us the information about the multiplicities and lambda when the diagram of lambda is contained in a horizontal strip of length d. But our algebra, okay, UTN of E is not finite generate algebra, so we cannot capture all the multiplicities and lambda using our horizontal strip. So for this reason, we need, okay, if we want to know all the multiplicities and lambda, capture all the multiplicities and lambda, we need to find a new method. And this is the method 2. Okay? So the method 2 is based in two results. The first result is the Almizur and Rayev. Say that if you have a Bay algebra, okay, then exists K and L non-negative integer, so that if you suppose that L lambda is different to 0, this implies that the diagram of lambda is contained in a cube of this form. So we need to find a method that gives us information about the multiplicities and lambda when we work with a big cube like that. Okay? The second result is like a generalization of the result of Drensky variable. This result gives us a relation between co-characters and the double Hilbert series related to this algebra. So, if you can write this double Hilbert series like this sum, the coefficients and lambda are the multiplicities for the co-character sequence of the algebra A, when lambda is contained in the cube K. So we need to find the double Hilbert series related to UTN of E if we want to know these multiplicities. And we did that. So the first step was to find an expression for the double Hilbert series of this algebra, for the Grassmann algebra. In the previous case, this case was done, but in this case, we didn't know this expression. So we have to compute, and it's given by that, okay? After that, using induction over n and a similar result of Formanek, we can find the double Hilbert series for this algebra. But again, okay, this expression is so complicated, so we need to find an easy way to write that. But remember that in the previous case, we worked with multiplicity series instead Hilbert series. And in this case, we did the same. But we need to generalize the concept of a multiplicity series. Okay? So, for this, given a partition lambda in this cube, we break this partition in three partitions, lambda 0, mu, and nu, like that. Okay? Lambda 0 is the part of lambda contained in this rectangle. Mu is this partition has almost k parts. Nu is the conjugate of these partitions, and mu has almost L parts. Okay? After that, we consider k and L non-negative integers, and we define this set. But note that this hue is the union of this set. Okay? And we consider three sets of variables, of commutative variables, and we consider the algebra of the power formal series in this variable. Okay? Finally, we define this set. This set is a vector space with this basis, and this set is a subalgebra of this. Okay? So, given the element in capital lambda KL, we define the KL multiplicity series like that. Note that here we use the composition of lambda in three partitions: lambda 0, mu, and nu. Okay? We use this decomposition. Okay, but note that for the second result of this method, the double Hilbert series of Pei algebra is an element here. So we can define the natural way the KL multiplicity series of a Pei algebra like that. Again, note that these numbers and lambda are the multiplicities in the co-character sequence of this algebra. So we need to find the KL multiplicity series of UTN of E. Okay? For this, we define the following operator G, okay, that is given by this expression, but note that this expression is the double Hilbert series of the Grassmann algebra. So we need to understand this operator, but it's very difficult, okay? It's like this operator. So for this reason, we define the operators G1 and G2. These operators has the similar role of the operators Y and Y hat in the previous method. And study these operators is equivalent to study the operator G, because G can be written in terms of this operator. Okay, so we study these operators instead. Okay? And the action of this operator is given by the Young rule. Okay? And we obtain the following result. The first result is the description of the action of the operator G1 that is given by that, for that, sorry. And the second result is a similar result, but for the operator G2. Okay? This can be proved using your. And after that, we have these operators, and we have the expression for the double Hilbert series of UTN of E. Then we can calculate the KL multiplicity series of this algebra, and is given like that. Remember that G is given in terms of the operators G1 and G2. Finally, using this theorem, we can calculate all the multiplicities n lambda for any n. Okay, we compute some particular cases. So, okay. We make some computation for particular cases, but remember that in the previous method, we compute for UTN of E, we compute K and L, okay? K is equal to N, and L is equal to 2N minus 1, okay? So, if we want to compute all the multiplicities for this algebra, we have to work with this n to n minus 1 multiplicity series. Okay, so we have the Grassmann algebra, n is equal to 1. So this implies that k and n are equal to 1. So we computed the 1-1 multiplicity series of the Grassmann algebra, and is given by this expression. Okay, and this expression has all the information about the multiplicities n lambda. Okay, after that, we have to write this multiplicity series as a power series in these variables. Okay, and we did that. That is given here. Is given here. Note that the multiplicity series here, it means the coefficients are equal to 1 for all the terms. And we recover all the result of Olson and Reher. Okay? After that, we work with the 2-3 multiplicity series for this algebra, that is this case when n is equal to 2. And this multiplicity series is given by this expression plus this expression. Okay, so in this expression we have in this expression okay, 1 second. In this expression has all the information about the multiplicities and lambda for this algebra. After that, we have to write this multiplicity series like a power series in these variables, and we obtain the explicit form of these multiplicities. And we recover all the result of centroid. Finally, we compute the 1-1 multiplicity series for UT3 of E. Okay? So this multiplicity series gives us the information about the multiplicities and lambda when the diagram of lambda is a horizontal strip or a vertical strip, okay, or has this one. Okay? These three shapes. And the multiplicities and lambda are given by this expression. Okay, if you want to capture all the multiplicities, you have to work with the 3-5 multiplicity series. This implies that you have to work with 11 variables. But the method works, so it's only make the computation. Of course, the computations are not easy to do. But we can use software like Maple or Mathematica that help us to make algebraic manipulations. I want to finish with this remark. Okay, if you want to only know the partitions, the multiplicities in lambda for partitions with only d parts, okay, with fixed numbers of parts, you can use the method 1. But if you can calculate the multiplicities and lambda with more freedom, this means that lambda is a partition with a limited number of parts, we have to use the method 2. Okay? With that, I finish. So thank you. Sorry for my English. I hope that
questions? Comments? No questions?
I can add some comments about
Okay.
history because there was some history there. You see, there were both talks there spoke about the changing but in different languages. Somewhere in 1950, so 73 years ago, 2 papers appeared, but both were, for the modern mathematicians, it were written in rare languages. So very few people have read this. One is in German and the other is in Russian. And the paper in Russian, this is by Anatoly Maltsev, when he started to apply explicit computations with the symmetric group. And the other paper by Specht is almost mainly known for the theory of representativity of the symmetric group, but he has one paper about another topic, about PI algebras, which is with a very big influence. He put the question about finite generation, the so-called Specht problem, or finite-based problem, but also he showed that in both papers the representation of the symmetric group were used very actively. But until the late 70s, it was all the people they worked with the symmetric group. But in many places in mathematics, also in physics, they use simultaneously representation of the symmetric group and the general linear group. And when they saw this with Berel, we independently decided that in the other case they use both representations, while also we should use the same idea. And it turns out that in both cases, if you know the representation of the symmetric, the general linear group, you get free. What happens with the representations of the symmetric group. And it turns out that from a computational point of view, this is a big advantage because you work with finite number of variables instead. For example, if you want whether something is a polynomial identity, you should consider a vector space of dimension n factorial and to replace here with some elements. But in some cases, it's more convenient to consider only 2 or 3 variables. So, from computational view, this is a big advantage. Also, in some moment, Berel and Hegel decided that we can use it instead of symmetric functions, supersymmetric functions, which gave the information about the two things. And also, from computational point of view, there is a paper from 1903 where the paper is devoted to how to solve linear Diophantine equations in non-negative integers. And it turns out that this works very well if you have a symmetric function in a very special kind. And in the case of PI algebras, all these functions there is so nice. You can apply this method in 1903, and you can get the explicitity, you can write easy computer programs, etc., etc. So all these things was involved here. So here you simply use also some calculus, not only representation theory, also some computation with Maple, with Mathematica, and so on and so on. So this is also you have some impact in the other direction. For example, the things of Frege, it turns out that they have applications to analysis, not only from one side but from the other side. So this is really something which you need a lot of things to know to get something, but it's really very exciting to do this together.
Okay, thank you very much. And thank you to all speakers today. And thank you to
So this was the last term of our conference. I would like to thank all the participants for attending this conference in mathematics in Southeastern Europe, especially to thank all the speakers